So today's question is all elements in two binary search trees. So we are given two binary search trees and their roots are given, and we have to return a list which contains all the integers from both trees sorted in ascending order. So for example, if two trees were 214 and 103, then basically the elements will be 214 and the elements in second tree will be 103, and when we merge them we have to return the sorted output. So basically we merge these two lists and we sort it. Right, so how to do it? So basically I'm following the approach which is given in the hint itself. So let's read the hints. Traverse the first tree and like populate list 1 and the second tree in list 2 and just merge those two trees and sort it. Right, so we will do this. So let's see, somehow we can do something like this. Const list 1 is equal to let's say it's empty and we'll populate it. So let's say populate list 1, populate node root 1 and then populate list 1 with that thing and const. So you can also return a list from this function, but I'll do it this way. So from root 2 we want to populate list 2. Alright, so how will we do this? So suppose my tree looks like this, so I will recurse basically. So I'll try to populate my list with the whole tree, and what I can do is I can just take a node out and we can populate with the left subtree and right subtree. So basically we are having a problem of populating a list with this tree, right? So the smaller problem is for this left subtree and right subtree. So that is what we will do. We will use recursion to do this. So how do we implement this function? As I said, so if I have a node and if I have a list to populate, if node is not there, so basically if node is null, we have reached some child of leaf node which should be null, then we do nothing because we don't have a value to add. Otherwise, as I said that we want to recurse, so first we take this node out. So we push the value of this node. For example, if I'm looking at this one, I'll add 2 to the list, but then I'll recurse on left and right subtree. Then that is easy if you understand recursion in this case. So node.left and list and populate node.right and list. So as I mentioned, I'm recursing on the smaller problem, which is left subtree and right subtree from the bigger tree. So take that root node out and recurse on left and right, and the base case is when you reach a leaf node, its children will be null. So when that happens, we will just return and do nothing. So that's how this recursion will end. So after this, list 1 and list 2 will contain the elements of root 1 and root 2. So we can just verify that once. So the element should actually be similar to something like this. Right, so 214103, we got it. So let's try to increase the size of these array. So let's see if this works. So if I do in order traversal 1, 2, 3, 4, 5 should be okay, I think. And then we have 3, then we add, let's say, so we have 0, let's say we add minus 1, and let's say we add 1. So let's see if we run this. So we have duplicates also in this case. The root 2 is not paste. 1 0, so maybe because 1 0. I have to change too many things now. So 2. So now this should be BST. Right, so what we are getting is 214 and then 35. And then 35. Okay, and in second case we are getting 20 minus 1 20 minus 1 13. So if we look at this, first we get 2 and then we try to recurse on left and right. So when we recurse on left we get 0, then we recurse on its left we get minus 1, and then we recurse on right, which is 1, and then we come back and we recurse on the right, which is 3. Right, so that's how we are getting this order. So basically, just to repeat, I go to a node, I push it, and then I recurse on left and I recurse on right. That's how we are getting this order. Right? So that is what we did. We populated these lists using this function, and now we have those lists. We do what the hints tell us. We merge those. We merge list 1 and we merge list 2. We merge list 1 and list 2, and then we sort the merged list, and then we return the answer. So that's it. So basically the thing which we needed to know to solve this question. So sort is generally inbuilt in your languages, and merging list is not that difficult. You can use iteration as well. So and so this is the only thing which you need to understand. So this is a recursion. Now what we do is we run this. So basically I'm not printing them anymore. So this should be merged now. This should be sorted minus. So this is our answer, minus 1 0 1 1 2. So if we see it, there is no diff. So we'll just try to submit it, and then we will try to see if we can improve this solution somehow. So this is accepted. Oh, okay. So that was my previous acceptance. So this is accepted because we did exactly what question asked us to do. Traverse the first tree in list 1 and the second tree in list 2, merge the two trees in one list, and then just sort it. So that is exactly what we did. List 1, list 2, merge, sort, and return. Right? But there are some things which can be done. So we'll just try to look at the complexity. So this is linear. So because we are traversing this tree recursively, so what we are doing is we are going to one node, then we are going to its subchildren, and in each node we are just using this constant time, assuming that list per push is constant, so we are doing only one thing, so it will just do this one thing for all the nodes, right? So this should be linear in size of tree 1 plus tree 2. This should be linear in size of tree 1. This should be linear in size of tree 2. Then we are merging them, and then we are sorting them. So this will actually take, so suppose n was the total length, then this should take, like in standard libraries it will take n log n time, depending on this implementation, but generally it's n log n, right? So so this is what, so we can actually improve this complexity a bit. So I'll tell you how. So one thing is that these nodes values are actually in a particular range which is not very big. So you can represent this range in your memory, and you can use a sorting technique. So this will generally be this is the implementation, but you can use a sort technique which is called count sort, which will take memory which is max number, but it will run in, it will basically run in this time max number, which is 10 raised to power 5. Right, so this should also pass. So the total number of nodes can be 10 raised to power 4, so we are doing it into 10 raised to power 5, so should be okay, right? But n log n will be a little bit bigger, I think. 10 raised to power 4, cool, it should be comparable, but right. So this is one way in which you can do linear. There is one more way in which you can do linear, so that is so that in that we will use one property of binary search trees, that you can, so how binary search is made, it actually contains the order of element inside it, right? For example, even if you start looking from left side, right, on the leftmost node there will always be the smallest element, and if you go to its parent, it will be the next bigger, and bigger to that will be on the right side of that node, kind of. So if you think about that, so there is one more way of populating that list, which will just give me the sorted order. So for example, if you look at this 1 2, so if you look at this tree, so 2 0 3 minus 1 1, so let's imagine what will the sorted order will look like. So it will look like -1, then it will go to 0, then it will go to 1. So basically first it look at the left child, then it look at the current node, and then it look at the right child, right? So after that, so after 1 you will actually go to the node 2, and then you will go to the 3. So whatever happened here, like left node, current node, so suppose we were looking at 1, so left node, current node, and right node. But then if you start looking starting from 0, then left node, current node, and right node. So this kind of traversal in binary search tree, it's called in-order binary traversal. And when you do in-order binary traversal, the list you get is actually sorted. So let's just try to do this. How do we do that in-order traversal now? So right now what we are doing is we are doing current node first, left then, and right then. So if you can see a little behind, current node, left and right. But for in-order I told left node, current node, and right node. So that means left node, then current node, and then the right node. So this is the only change we need to get a sorted list. So let me just show it to you once. So I'll just print. I'll print list 1 and list 2 to tell you that what is the order in that list. So this is the list. I'll just print it and I'll make my change and I'll show you if it is sorted later or not. So it is not sorted because 1 should be before and like 3 should be before 4, something like that. But if I just change this, so you can read about in-order traversal if you are not able to understand. So it is called, so I'll just write it down for reference, in-order traversal of tree. So in-order traversal is valid for any tree, but in BST, in a search tree, it will give you a sorted order. So I changed this. We had current node before, but processing the current node will go here. Right? So now if I print those two lists, so now they are giving something like, so members are the same, but now they will be sorted. If you see 1 2 3 4 5 minus 1 0 1 2 3, right? So above it was not sorted, and because we just used that property of binary search tree and used in-order traversal, we are able to get sorted list. So now I know in linear time, we did not change any complexity here. So it is again in linear time we were able to get sorted list. So now there is one popular or very useful subroutine which is called merge sorted lists. So this is a very popular subroutine which is used in merge sort. So it's a good algorithm or a good technique to know. So basically what it can do is it can do this step in linear time, right? So this linear time as in sum of sizes of list 1 and list 2. So we will try to do that, and it only works when both lists are sorted, right? So we will implement this. Merge sorted list 1 and list 2, and this will be now in linear time, right? So we will try to implement this and we just return the answer. So let's try to implement this function merge, and you should try to like learn how this thing works. Alright, so we are merging two arrays, and let the output be answer. So this will be our output, and now so what we will do is something kind of 2-pointer kind of thing, where 1 pointer will be in this array and 1 pointer will be in this array. So we start with my pointer at 1. So let this be my pointer, and sync will do this. So my pointer is starting at index 0, and my second pointer will be at index 0 of the second array. So now we will move these pointers. Right, how we will move this, and whenever, so basically when we are looping over these arrays, somehow we will ensure that these pointers only go forward. Basically they never go forward, and we see all the elements. So that's why, because these pointers will only go forward, and in every iteration I'll write a loop in which in every iteration either one of them will go forward, right? So we have two conditions. One is like one of them will go forward, actually only one of them will go forward, and never any of the pointers will go back. So that what happens is in every iteration we are guaranteed that pointer will move forward. So that means it will only take at max the length of this one plus length of this one to complete the traversal, right? Because we are never going back, and we are always going one step forward in either of the array. So that is what we will implement. Let's see how we will implement it. But what we will do with these pointers, so basically we know that these are sorted, right? So we know that the smallest element will be on the left. When we look at these two elements, we will just pick the smaller one of them, because smaller of the smallest will be the smallest in answer, right? So we will pick -1 and we will push this pointer to the second element. Why? Because we know that, so when we look at both of these two arrays, who is the candidate for smallest element? So whoever is the smaller of the smallest of these two. Now this candidate is out. Who can be the next smallest element? So that can be like, this is still a valid candidate because this is smallest in this one. Anything else in this array will be greater than this one. So from this array, if anything has to come, it has to be this one. But from this array, this has gone. So anything which can come is the next one. So we move the pointer to next. So we get 0. Because we chose from the second, we will move it forward. And suppose without any loss of generality, we are giving second array benefit whenever they are equal. So I'll take from second one, or we can do first one as well. So we take the second one and we move this again. And now the candidate are 2 and 1. Now because we are choosing from first array, because 1 is smaller, we move this forward and not this. Right, so this stays at 2, and that way in every step we will be taking one minimum element from both of them, and finally the answer array will actually have the sorted order. Right, so that is what we want to do. So what we are doing is index in A is 0, let index in B is also 0. Then what we do is while true, and till when we will do this, while we will do, so basically you can write this condition in while as well. While, okay, I'll write it. So okay, I like how this looks a little bit clean to me, but yeah, so you should write this condition in while loop actually. So while index in A is less than, so we need lengths of them, so const length of A is equal to A dot length const length of B equal to B dot length, right? So now index A should be less than length of A, and if index in A is equal to, and index in B is equal to length of B, if they somehow become equal, that means both of those pointers are here. So one pointer is like after 5, that means we can't read anything, and second pointer is after 3, which means we can't read anything. Then we can just break, right? So you can write negation of this in while, and then what we do is we try to see which one is smaller, right? So to see which one is smaller, so I will implement it in a particular way. For example, if first pointer has reached its end and second pointer is in between, for example, like suppose we have a condition like this, then we know that from the first array we don't have any candidate, right? So there are multiple ways to solve it. Like one way is you detect that if you have reached end of any array, then you can just add the remaining portions. For example, if you reached this pointer, when it will reach 3, right, this pointer will still be here because 3 and 3, right? So now you know that you will never get any candidate from second array. And now at that point, what you can do is you can just add the remaining portion of first array into the answer, right? So I'll just repeat, when pointer in any of the array has reached to the end, then we know that there is no more candidate from that array. Then we can just append the remaining portion of the array in which the pointer has not reached the end to the answer, right? So that is one way to implement it, but I implement it in a different way. So I generate a dummy candidate. So basically, why are we not able to take any candidate? Because there isn't one. So I will generate a dummy candidate which will always be greater. So what happens then is we will always select from the smaller value, so the array where the pointer is, right? So how do we generate which is the dummy candidate which is never smaller than anyone? So you can use max value in your language. I'll use this thing, that candidate in A is equal to infinity, and let candidate in B is equal to infinity, right? So these are my dummy candidates. But if pointer, this index in A is less than length of A, that means we can still have a candidate. Then we don't need this dummy candidate. It's equal to A of index in A. Right, so what I'm doing is, for example, if we were in B, by default the candidate will have value infinity, but if the index was less, that means that we actually have a candidate and then we override it. So that is how I am solving this thing. B is less than length of B, then candidate in B is equal to B, then index in B. Right, so that's how we get it. So now what we do is we just take the minimum of those two candidates and we move the pointer in that thing. So if candidate in A is less than candidate in B, so that means that this pointer has to move and we have to push candidate in A. As I said, we will be pushing the minimum of those two. So we push the minimum and we have to increase the index, so pointer has to move. So plus equals 1. Right, and similarly we have to do exactly same thing. So we are giving preference to B, that if both are equal then we will take from B. So now else answer dot push candidate in B, and we increment the B's index. Right, so we just see what we are doing here is like if so basically as I said, whichever candidate is smaller, we just push it. And you should understand that this dummy candidate thing is just a way to solve that problem when one pointer has reached end. Otherwise in other implementations you might see that they are looping over the remaining portion and just appending it. And now we can just return the answer. Whenever this is finished, right, whenever this breaks, we know that we have always picked the smaller element and appended it to answer, then answer will be sorted. So let's just try to run this. So merge sorted list and my function name is run. Right, so this is A and B, and then run. So we showed if, so it is correct, right? So I'll just submit it, and if it fails, we'll fix it. So this is accepted. I'll just explain once more. So we did exactly what question told us, that form a list from first tree, second list, from second tree, merge that and sort it. Right, so we did that first, but then we realized that it's a binary search tree. Then we can actually get list in a particular way, which will give me that list in a sorted order, which is in order traversal. We look at left first, then we look at the current value, and then we look at the right. So this will give me sorted order. And if you don't understand this, search about in order traversal of binary search tree. Okay, so now list 1 and list 2 is sorted. Then we use the function which is called merge sorted list. So if there are two lists which are sorted, this can merge it in linear time. And so basically that's how we were able to reduce the complexity to linear. And then we just merge those two sorted lists, and that is our answer. Right. So that's it for this question. But there is one more thing which you can actually do, is you can try to solve this problem in place. If it is possible, I'm not sure, but that might be quite implementation heavy, so I'm not covering it in this video. But that will be a fun exercise to do if that can be done. But yeah, awesome. So that's it for today. Hope this was helpful. Thanks.